Now sometimes when we're designing microwave devices, particularly filters, we're likely to have inductors and capacitors that are both in series or parallel that are connected into our transmission line. So here's ZL. Let's say that this is length L. Here's my inductor L, and this length is going to be negligible. Here's my capacitor right there. So the way that we would handle a problem like this is we would plot ZL. Of course, that means we need to normalize and plot ZL. We would rotate towards the generator a distance L. And then, because we have a parallel element here, we would convert ZA to YA. So right there's the A point. And then we would calculate the admittance of the capacitor, and point B, YB, I'm going to write that B is right there, would be equal to Y of the capacitor plus YA. Remember that both of these are in mhos. Don't forget to denormalize. And denormalize means that you multiply by Y naught, which is 1 over Z naught. Now that we've calculated point B, we have YB, but we need ZB because we're going to add it to another element in series. So convert YB to ZB by translating through the center of the Smith chart. Make sure that that is normalized when you put it on the Smith chart and that it's denormalized when you bring it off. And then calculate calculate Z of the inductor, and our input, Zn, is going to be Z of the inductor plus ZB. Now let's consider one other major aspect that we need in order to do single stub matching, and that's the stubs. The idea of a stub is that we have a transmission line that is either short-circuited on the end or a transmission line that is open-circuited on the end. So here the load is 0, and here the load is infinity. What we're going to control is the length of our line L in order to get the input impedance that we want right here, Zn or Zn. If you refer to 2.7, section 2.7 in your book, this is referred to Zn of a short circuit, and this is Zn of an open circuit. So if you have a short circuit, Zn of a short circuit is equal to J Z naught tangent of beta L, and Zn of an open circuit is equal to minus J cotangent of beta L, and there's a Z naught in there. In all cases, we may want these transmission lines to act like an inductor, or we might want them to act like a capacitor, which is minus J over omega C. By controlling the length of each of these transmission lines, I can create either an inductor or a capacitor with an open-circuited or a short-circuited transmission line. Now, in the case of stub matching networks, what we're going to be doing is taking our load, ZL, and then the first thing that we're going to do is rotate a distance d to fix the real part. And the real part that we want is 1. So right here at point A, we want ZA to equal 1 plus J something. And then we're going to add in a stub. Right here, either an open-circuited stub or a short-circuited stub, such that YS is equal to minus JX. And then the input, ZS. The input impedance, Zn, is then going to be the sum of these two, which is going to be 1 plus J0, which is matched exactly the way we want it to be.